This one real quick and get ahead of the game. So what we're looking at here is entropy for kind of the thermodynamics second law. We've talked a little bit about entropy in class and how it's the disorder of a system. We've talked about kind of dropping plates and how they shatter, but you never see a plate that is shattered recreate itself and stick itself back on your table for dinner time, to the unfortunate dismay of many. But one thing we've only talked about kind of briefly is an equation for entropy. And an equation we have for entropy, which entropy is designated as an S because, E is just too nice of a word. But a change of entropy, or a delta S, is equal to the energy, Q, or heat energy flowing into or out of a system, divided by the average temperature. And I'm going to really highlight that this is an average temperature here because we're going to see why that's so important just in a second. This idea of a natural process trying to shift to a state of greater disorder or entropy here was actually thought of originally by Clausius in the 1860s. So the idea has been around for a while. It's not something we just pulled out a month ago. But we have this equation here, delta S equals Q over the temperature average. A few important things to note about this equation is that this Q, it is the heat added by a, quote, reversible process. Okay? And by that we mean if you had like a PV graph or something, you can kind of like slide on it or slide back. It's not something that's discontinuous. Typically, because this temperature is an average, T is a constant value, so to speak, within a problem because it's an average temperature. And it needs to be in Kelvin. And that's actually huge right there, that this needs to be in Kelvin. Okay? So if we take a little look at an example here of how we could use entropy to see the disorder of a system, let's actually take 50 kilograms of water, good old H2O, at 20 degrees Celsius, and mix it with 50 kilograms of water at 24 degrees Celsius. Okay? If we remember back to our calorimetry, or if we wanted to work it out on our own, we know that this water is going to reach an equilibrium temperature of 22 degrees Celsius. And that just kind of makes sense. You have the exact same water, the same mass of it, 20 to 24, we go halfway in between there, boom, it's 22. A lot of people think that our average temperature for our entropy is going to be 22 here, and it's not. We need to be a little careful about this. In this problem, we actually have two changes of entropy. We have one from the cooler water and then the second from the warmer water. And the total change of entropy here is the sum of those entropies added together. So our total delta S is going to be equal from the delta S of the cool water plus the delta S of the hot water. And we should note here that a delta S which is positive means that heat is going in, where a negative is heat that is going out. So let's take a look at this here. If we take a look at, because delta S is for each of these Q over an average temperature, we know the Q's for each of these. We know Q has to be equal to MC delta T. If we look at the cool water here, we'll do this in blue for the cool, we know its mass is 50 kilograms. We know the specific heat of water is 4,186. That is in joules per kilogram, Kelvin or Celsius. And because the Celsius or Kelvin, the difference doesn't matter here. This value here is 2, whatever you'd like it to be. If we map that all out, 2 times 50 is 100, which means we're getting some extra zeros off of this, which means we're getting, and I'll write it in slightly easier notation, 4.16 times 10 to the 5 joules. Okay? If we wanted to do this for the hot, MC delta T, because we have the same mass, same specific heat, and a nearly identical temperature shift, the only difference is this is a -2, we actually find that our Q is the same, but it's just a negative value. Okay, so this is actually negative 4.186 times 10 to the 5th joules for our hot. Okay, and that deals with the idea of the hot water is losing heat. The heat is coming out. So at this point, we just have to take Q over the temperature average, add them together, and be set here. So to find this total entropy, we need to take QC over the temp av, and then add it to the hot over the average temperature. When we do this, we get 4.186 times 10 to the 5th, and then this is going to be adding a negative quantity of 4.186 times 10 to the 5th. And a lot of people say at this point, hey, look, I've got the same number here, one's positive, one's negative. I should have the same T average. The entropy is going to be 0. And logically, that's kind of what you want to believe. This cold water has gotten warm by the same amount that this warm water got cool, so the entropy should just cancel. But that's not true. We've actually gained disorder in the system. And the reason being is because you have these average temperatures. If you think about the cool water, it was starting at 20 degrees and went up to 22. So its average temperature was actually 21 degrees Celsius. And if we convert that into Kelvin, 21 degrees Celsius, convert to Kelvin, we are adding a positive 273 to that. So that becomes 294 Kelvin. This is 294 Kelvin here. Okay, well that's not crazy. But for the hot water, it went from 24 to 22, which meant its average temperature was 23 degrees Celsius. If we add 273, we get 296 Kelvin. That's its average temperature, 296 K. Now if we look at this, because our hot has a higher denominator than the cool, it's actually a smaller number. What we have here is a large number, well, a larger number, minus a small number. Well, if we have a large positive minus a small value, then you are going to get a positive value, which means that you are actually going to be increasing your entropy here. When you actually math this out and run everything, you actually found that the change in entropy is approximately 10 joule per Kelvin, which is a little bit weird. It's weird to think about that, because you think that, you know, they should change by the same amount, the entropy positive and negative should cancel. That's not what we see. We actually see that we gained some entropy here just by mixing things and having them change by the same amount. We have gained disorder in the system. That's kind of an interesting thing, and it's something that's non-intuitive whenever you first do it, but it all has to do with these average temperatures that we care about, and that's why, you know, all the way back up here, that average temperature is something to really, really emphasize for that. Okay, but that's kind of how you can run an entropy problem. This is just straightforward. Your Q's are just MC delta T's, so they're just MLs for vaporizations or fusions. Then you're just adding them together. So with that, we're fin.